Problem number 13 is a highly conceptual question, but one that is often kind of tested. There's not a lot of math to be done here, but it's kind of sometimes confusing what you actually need to do. So we have some function g. We don't know what it is, but we know that g of 2 is 3. So the point 2, 3 is on the graph. And what we know is the derivative of g, its absolute value is always less than or equal to 4. So what that means is the derivative of g can only be as high as 4, and it can only be as low as negative 4. It can only be in between those numbers, because anything else would make this absolute value not satisfy this inequality. So our derivative is always between negative 4 and 4, meaning our slope is always in between negative 4 and 4. So let me graph what this might look like. So we have the point 2, 3 on the graph here. And what we're asked is, what is the largest and possible values of g of negative 1? So there's going to be some point over here at g of negative 1. We don't know where it is, but we can figure out what it could be smallest and largest based off of the fact that we know that the derivative is constrained. So think of it like this. If your derivative could be as high as 4, and that's the maximum that it could be, if you wanted this function to be increasing the fastest, that would just mean that your slope would be 4 all the way. Because if at any point you made the slope less than 4, you couldn't do that because you would have to make the slope greater than 4 to come back. So, in other words, we could have the slope that goes to this point, we could have a lot of different curves going through this point, as long as their slope never went higher than 4. But if we want it to be as steep as possible, we want it to be 4 all the time. So if it was a slope of 4, then it would be like this. I drew that basically right. On the other hand, if we want it to be in the other direction, again, we want it to be decreasing as fast as possible, the slope would have to be negative 4 the whole time if we wanted it to be as decreasing as extremely as we could. So that line would look like that, let's say. So anything that's in between those is a possible graph of g. But we want the extreme cases because what we're looking for is what's the smallest value that g of negative 1 could have. Well, g of negative 1 could be any number between here and here. Because what I just drew when I did these lines was, think about it like this. In choosing the steepest possible ways of this function existing, I basically indirectly did find g of negative 1 or g of anything. You could pick any number on here. Now you know it has to be in between two such values, or else that graph couldn't have existed because of this derivative constraint. So if I want the smallest value of g of negative 1, that's going to be the one that lies right on this line, because g of negative 1 is here. If it has to be in between here and here, the smallest one it could be is down here. So now we just need to know what that is. Well, that's pretty easy because I know this point is 2, 3, and this line has slope 4. That's why I drew it that way in the first place, because I know it couldn't be, like 4 was the biggest it could be. So this question really now is becoming, if you have a slope, or if you have a line of slope 4, and it goes through the point 2, 3, what does it go through at negative 1? Well, let's make the line and then just plug in negative 1. So if we have a slope of 4, and it goes through the point 2, 3, I'll just use y equals mx plus b to get my equation of the line, and then I can answer the question. So I know the y is 3, the m is 4, the x is 2, this would be 8, so therefore b is negative 5. So now my function is y equals 4x minus 5. That's the graph of this line that I drew here. So now the question, what's the value when you plug in negative 1? Well, let's just do that. So I get 4 times negative 1 minus 5. So the lowest value that g of negative 1 could have been, given this constraint in the beginning, is negative 9. So if g of negative 1 was any lower than negative 9, my slope would have had to have been more extreme than this. That's what this problem is really getting at. So once you're constrained by this, and you know your derivative could never be bigger or smaller than that, you know where points could be constrained between.
The Teaching Center, UF's Learning Resource Center.